Okay.
Hello, good afternoon, everyone.
Okay. It's kind of on, yes. Okay.
Hello, I'm Jing from the Hong Kong Polytechnic University. It's my pleasure to give you a presentation today talking about our AI-empowered digital twin for smart building management. The building sector is really important for the carbon neutrality. As a high-density city, Hong Kong, well, the buildings accounts for about 90% of Hong Kong's total electricity consumption and more than 60% of total carbon emission. And Hong Kong government has launched the Hong Kong Climate Action Plan in 2021 to committing that to reduce 50 to 20% carbon emission in 2035 and reduce 30 to 40% carbon emission in 2050. However, in our building energy management industry, we almost rely on the main power, rely on the experience from on-site operators, and also the outdated operating interface. Well, this is our past experience highlights from the management and from the management technologies achieved previous. We spent a lot of time, like couple of months, and we use the whole expert team to do these cases and achieve a lot of energy efficiency. However, if we use the art technology today, like big data, like AI, IoT, digital twin, etc., it could be more efficient and it could achieve the cost-effective mass deployment in the building management platform. So here we proposed a whole framework for the smart energy management. The whole framework could be divided into 5 parts. First, we collect all the informations like the spatial data, and the time series data from buildings. And then all these data will transfer to our database. And then we have our AI engine here, providing the optimal control strategy and predictive maintenance strategy. And the AI engine will send the AI recommendations back to our database, and then all the data, like the real-time operational data and our AI results, will send to our platform. Well, now we have developed the MR platform, like the glasses, the mixed reality glasses version, and also the Windows version. And we are now working on the mobile phone and iPad version. And here, we use the brick model as a standardized data description to describe and organize all these data. And here is our digital twin-based energy management platform. And we have made the mixed reality platform here and the Windows platform here. And I will show you the videos later. And currently, we are working on the mobile platform. And also, we work on the AI for the smart energy management, providing both real-time control and predictive maintenance. And we try to use our domain knowledge, like the design information, like our drawings, like our physical principles, to help the AI to be more efficient, more accurate, and more great and safety for the on-site operators. Here we cooperate with Hong Kong government. They try to, well, this is because the different buildings have different contractors, different devices, and all the data are maybe in different format and different transfer solution. So the government want to make a standardized description to manage all these data from the buildings. And we try to use brick model here to integrating the multi-source data from buildings and from all the systems in buildings. Well, finally, we try to make cost-effective deployment in buildings, try to save time, to save manpowers, and to make more fast deployment in buildings due to the data-driven nature. And here I will show you some case studies. The first study is from office building. It's a typical VAV system. It's an eyesight system, and we deployed environment control strategy here to control the VAV set points. You can see that from the historical control strategy, the local thermal comfort is there is a local thermal discomfort from the uneven air distribution from the all occupant zone. And we try to use AI to reset the VAV set point to make it more even. And here we try to describe the whole system and its environment from the graph-based data structure. Here we use the graph-based data structure to organize the airside system and its corresponding environment. And we use the spatial temporal indoor environment modeling here. We use GNN-RN model here to predict the indoor environment. And we try to use this kind of strategy to maintain a comfortable indoor environment in the whole space. Also, this strategy has been deployed in our mixed reality device. You can see the BIM model here. We mapping the BIM model with the real building. And you can see all the ducts and pipes behind the ceilings. And also you can see the real-time map, real-time temperature map, real-time operational data, and our real-time AI strategies. Here is a short video for this. But all these ducts and pipes are just matching with the real building. And we can see this show where you are and also show the real-time operational data and the environment data, and also our AI strategies. And it also enhanced the indoor navigating for users. Okay, and our next study is in the chiller plant. Like this, this is our well, in fact, PolyU has 8 chiller plants, and this chiller plant is one of the most largest chiller plant in PolyU. It's really complicated and assumed a lot of energy consumptions. Well, here from the historical control strategy, there are some unnecessary switching, like stage on and stage off, according to the rule-based strategy. Like if the temperature is bigger than maybe 14 Celsius, there will turn on another chiller. And if the temperature go back to the 12, they will stage off this chiller. So it costs a lot of energy, unnecessary switching here. And we try to use probabilistic prediction to predict the cooling load, different from the traditional point value prediction or like the single value prediction. We predict the cooling load as a distribution with probability. And with this prediction, we can make risk-based chiller sequencing strategy. And we deploy this AI-based strategy in the real buildings. Here is the two-way communication between our lab and the chiller plant. And we try to use a semi-automated control, like we automated send emails to the operator and try to let the operator see the AI recommendations. We trial like this about like half a year to make our algorithm better. And then we turn to the fully automated control. Like we have an AI mode in the BA system. And we just like a cloud platform, and we send all the recommendations directly to the chiller plant. And the BA will conduct our AI recommendations directly. Here is a preliminary result from this case. And you can see with the chiller sequencing strategy, we can save about 10% energy consumptions. And here is another study. We proposed both chiller sequencing strategy and the chilled water supply temperature set point reset strategy, two strategies. Well, this paper haven't been published yet, so I just to show you preliminary results here. It is a 6 weeks fully automated test in the real building. And we are still working on this case to test the performance of these two strategies. But you can see that the results showed a significant energy saving over the 2-6 testing. And this is the Windows version digital twin platform we developed here. And this is a short video. Okay, this is the homepage of our platform, and you can see all the key parameters here. And also all the real-time data and also historical data. And all the relationship of this data will be organized by the brick model I've mentioned before. And this is our AI recommendation. And this is the maintenance records for the whole chiller plant. Okay, that's our AI-based energy management platform. Thank you. Any questions? Yes.
Thank you, very interesting part. So, two questions. Who makes the decision increase or decrease the temperature, for example? Is it recommended by the AI tool, or it is like a human operator that eventually decides to adjust temperature? And the
You
second
mean
question
the-
is that how generalizable your algorithm algorithm thinking?
Okay. For the first question, you mean the historical control strategy or the AI-based strategy?
AI is
It's all from our AI engine, and we will send the AI recommendations to the BA system, and the BA system will directly conduct our strategies. Yeah. And for the second question, yes, it's a great question. We try to make the cost-effective mass deployment to all the buildings, and in fact, we have tested the the case study here for the number 2 case study. We developed almost like 1 year to the AI strategy to refine our strategies. But for this study, we just spent 2 weeks after the two-way data communication to deploy the same strategy in another building. Thank you. And in fact, we find the most difficult part is the data communication, not the AI strategy itself. We spend a lot of time for the communication with the from the chill plan to our platform. Yeah.
Do you have to install a lot of extra monitoring in the plant to enable? Do you have to install a lot of additional monitoring in the building or the chiller plant?
We install a gateway here. We just need a gateway to complete the two-way data communication.
Was there additional?
What?
Was additional monitoring installed on top of what was there already to enable the development of digital twin, or was the existing monitoring systems enough?
Well, in fact, for all the buildings today, we have the BA system. It's like the building automation system. I think most of the building already have this, and we just make our cloud-based service on top of this. So we just need a gateway to do the data communication and then send and do all the calculations and AI things in our lab, in our servers, and then send the results to the BI system, and the BI system will conduct all the strategies. Thank you.
Thank you.
Let's sign our student way. Our next speaker is Subhash Kumar, presenting optimizing AI generating for a power system by
This actually means that there's a father. What the second name of that?
Okay.
Okay. Yeah, lines, like the animal, but different.
Yes. Organ.
Okay.
Let me close the list.